Hello class, and thank you for watching. In this lesson, we're going to go over the first parts to section 5.5, zeros of polynomial functions. The learning objective here is to know how to identify two of the remaining three zeros to a polynomial function, to a cubic polynomial function, given that we're provided one of them, provided one of the x-intercepts. Now, from the factor theorem, we know that if f of x is a polynomial function and x minus c is a factor to that polynomial, then that means that f of c is going to end up equaling 0, and vice versa, that if f of c is equal to 0, then that means that the factor of x minus c, or the binomial of x minus c is going to be the factor to the polynomial function f of x. Now, because of that statement, then when the following five statements are also going to be true to the fact that x minus c is a factor to the polynomial. The first one would be that x equals c is a 0, x equals c is a solution, or we can refer to that x equals c is a root to the polynomial, to the equation f of x is equal to 0, or to the function f. Now, we can also note again, because all those things are the same, that in terms of a graph, x comma 0, or again the coordinate c0 is going to be an x-intercept to the graph of the function f. So let's look at an example of how we use the fact that we're given one of these 0 solution roots and find the remaining two zeros, the remaining two x-intercepts to the graph of f. So in this example, we're provided with the fact that this function has a factor at x minus 3, which means that using the remainder theorem, and I evaluate the function at 3, the remainder is going to end up equaling to 0. So this is what we're given, again, what we're provided with. So using that fact, that would mean that if I use synthetic division, I can get the quotient to this. The quotient of this polynomial is going to be a factor that when multiplied with x minus 3 equals again to that value there. So let's figure out what that quotient is. So since 3 is the value that makes the polynomial equal to 0, synthetic division, I'm going to write the number 3, again, the opposite of this value, which is this number right there. And on the inside, I'm going to write the coefficients to my cubic. So 1, 2, negative 29, and positive 42. And I'm going to do the procedure of synthetic division. So I start by bringing down the 1, and I multiply. So this is 5. I multiply. This is a total of negative 14. I multiply, and that's going to be a total of negative 42. And then I add, which gives me 0. Okay? So this quotient, x squared plus 5x minus 14, multiplied with this x minus 3, is going to equal to that. And since the idea is to find the zeros of this thing, when is this thing going to cross the x-axis? I already know that that's going to happen at x equals 3. I just need to figure out what are the remaining two by figuring out what makes this now equal to 0. So using factorization, I can break this up into factors. I would find the factors of 14, which are 2 times 14, 1 times 14, I'm sorry, and then 2 times 7. Our signs have to be positive and negative, so that would have to be a 7 and a 2. So what are the two values of x that make this equal to 0? Well, for the first parentheses, I would have to plug in a negative 7 in order to make that entire thing equal to 0. And in the second parentheses, I would have to plug in a positive 2 to make that equal to 0. So here are the two remaining zeros, your two remaining x-intercepts to this function. So let's try now this example. So in this example, similarly, we have this polynomial function. We're given that the factor is x minus 5. We're given one factor, x minus 5, which means that f of 5 will make this entire thing equal to 0. So our objective here is to figure out what the other two zeros are, what the other two x-intercepts are to this function. So using synthetic division, we're going to figure out the quotient. 1, negative 11, 35, and negative 25. And we're going to write in 5. Again, this value right here. because this is the number that makes it equal to 0, so that's the number that goes out here. on synthetic division. So we're going to bring down the 1, multiply, add, multiply, add, multiply, and add, and we see that the remainder is 0. Now, since we're given x squared minus 6x plus 5, this factor multiplied with this is going to give us this value right here. And since we're looking for what makes this equal to 0, well, this times this also is the same thing. We already know what makes this equal to 0, positive 5. Now we have to do is figure out what the other two are, and the other two values of x that make this quadratic equal to 0. So let's try factorization to find those two values. So we have x minus, x plus, and since 5 is a prime number, it could only be divided by itself. So 1 times 5 are the only factors. So this should work. And it does. I just made a mistake on my sign. This should also be negative because a negative times a positive is negative. So that should be, so here are our remaining two x-intercepts. X equals 5 and 1. And since 5 is already being used, again, we're looking for all the distinct ones, okay? So it has a multiplicity of 2. So here, there's only one other place that it's going to cross the x-axis, which is at positive 1. When we graph this thing, we're going to see that it has a multiplicity of 2 that's going to be tangent at that location. So this graph that starts from down here, because this is a positive value, the right end goes up, the exponent is odd, so it's going to go down. It's going to cross the x-axis at positive 1, go up, go down, and then touch the x-axis at 5, and then move back up. So at 1 and at 5. And again, I know I'm tangent because x equals to 5 2 times. Here, that's once, and then we found that it equals to 5 a second time. So it's going to be tangent at that location. Okay, let's now turn to the back page. Now let's find again the two remaining, this time irrational zeros of f of x, using again the given information. So we have a polynomial function. Make sure that you write a 2 right here because that technically should be a 2 in order for this to work. And we're given that x equals 3 as a solution to, again, this equation, meaning that this is equal to 0, and we know one of the solutions, x equals 3. Now to find the other two solutions, we're going to set up the same way. We're going to use synthetic division to get the quotient to this polynomial when we're going to divide it by x minus 3. So since x is equal to 3, that's the value of x, again, that makes this equal to 0. So that's the number that goes outside here in this division problem. And let me zoom in, back in, and we're going to write in the following values inside the division box. So 1, negative 14, 47, and positive 14. So our technique is to drop down the 1 and multiply and add. Multiply, what is this, 33. Hold on, there's a mistake here. This right here should not be 3. That should have been the number 7. I made a mistake there. That was a typo. So I have two typos in this problem. So I need to go back and fix that. If you do not have that on your handout, it should be already fixed. If not, fix it for me, okay? So this should be a 7. So this would be a 7, which would be negative 7, negative 49, which is negative 2, and negative 14, which does then give us a 0, okay? So now we have the quadratic equation x squared minus 7x minus 2, and we need to set this equal to 0. And like before, we would try to use factorization, but we're going to come across a problem this time. We're going to see that factorization does not work because the factors of x squared are x and x. Our signs will have to be minus and a positive, and since 2 is a prime number, the only option is 2 and 1, and that doesn't give us that middle term right there. So this technique of factorization is not going to be the proper way of figuring out the two remaining ones. So we have no other option other than having to use the quadratic formula. So let's look at what the quadratic formula is, and let's plug that information in there, okay? So this is not going to be helpful. So let me move this downwards, and we cannot do factorization. And let me erase this because we don't need that, okay? So since factorization didn't work, the only way to solve this equation of what are the two remaining x values that make this quadratic equal to 0 is going to be to use our quadratic formula. X equals, which is that x equals to negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. So negative b means the opposite of our b value. Our a and b and c value are the following. A is equal to 1, b is equal to negative 7, and our c value is negative 2. So we're going to get those values from right there, okay, which are the coefficients in our quadratic equation. So now plugging those into the quadratic formula, all right, notice I'm saying a different thing there. We're going to get the following. So the negative of negative 7 is positive 7. So we're going to put that there. Plus or minus 7 to the second power is going to make it positive because that's going to be negative 7 times negative 7. So that's positive 49 minus 4 times our value of A times our value of C, which is negative 2, divided by 2 times the value of A, which is just 2. Now, in this situation right here, because again factorization didn't work, all we need to worry about is simplifying. In terms of simplifying is finding again the discriminant. What is this discriminant value going to equal to? So let's find out what that discriminant equals, and we're going to write that still inside the square root. Now that equals to a total of 57. And since the square root of 57 is not a whole number, this number is not a perfect square, we're not going to take the square root of 57 because there's no need. Again, it's going to give us a decimal value. So we're going to we want the exact answer. So our exact answer is this, that x equals to 7 plus the square root of 57 divided by 2. And the other option is that x equals to 7 minus the square root of 57 divided by 2. Now you could either use this format and write your answer like this. And to insert this symbol, you just simply have to put a plus and then immediately click on the minus key and this symbol will appear. Or if you can't figure out how to insert this symbol here, on your homework, you can write it as two separate answers. You could write 7 plus the square root of 57 divided by 2, comma, and then 7 minus the square root of 57 divided by 2. So that's another option as well. So you could either write your answer like I said on the left, or you could write it the way I have right here on the right side. Okay, so let's try this one again. So let's try this idea again. So here we have our polynomial. There's no errors on this one, nothing to make corrections on. And we know that f of negative 9 is equal to 0, which means that x plus 9 is a factor, okay? Remember again those statements that we talked about earlier in this video, that all these statements are equivalent. So if f of negative 9 equals 0, that means that the factor is x plus 9. Not that it's going to be useful or anything right now, just again reviewing just vocabulary and terminology. So let's figure out what are the other two irrational intercepts that's going to make this equal to 0. Now you can easily just plug this into decimals and try to figure out where the x-intercepts are. But since these are going to be irrational, that's going to be a problem when doing the homework, because the homework is only going to accept exact values, no decimal values. So at least it gives you a guideline that you could try to see if by then typing in your answer like the way you have it in the previous one, if it gives you if it equals the decimal values that you got on decimals. So let's do this one. from start to finish. So here we are given that f of negative 9 is equal to 0, so that's the number that we write outside our division. We don't get the opposite of that since we're already told what that number is. And on the inside, we're going to write 9, 78, negative 31, and negative 36. And we start by bringing down the 9. 9 times negative 9 is negative 72, which gives us a difference of 6. This is going to be a total of sorry, I messed up. This is 81, negative 81, which changes this number to a negative 3. So this is now 27, which is now negative 4, and negative 4 times negative 9 is positive 36, which is now 0. So here, I'm not going to even bother looking at trying to figure out the factors. I'm going to just jump straight into our quadratic formula because this one works every single time. So let me write that. Give me a chance to write that and include that here. And let's plug in the values. So the negative of negative 3 is positive 3. Now that negative 3 to the second power, that's going to give us the value of 9 minus 4 times the value of A times the value of C. And then 2 times the value of A, so 18. Because our value of A is 9. So 2 times 18 is, 2 times 9 is 18. Now let's simplify this again. Simplify the discriminant. Let's identify what the discriminant equals. So 9 minus 4 times 9, that's going to be 36. And that negative 36 times negative 4. That's going to end up equaling to a total of 153. So x equals 3 plus or minus the square root of 153 divided by 18. And again, since the square root of 153 is an irrational value, again, does not equal to a whole number, we're not going to bother taking the square root of that and using the decimal value. So here are your two answers. We have the first answer, which would be 3 plus the square root of 153 divided by 18. And the other answer would be 3 minus the square root of 153 divided by 18. So there are your two remaining x-intercepts. Now, in this last example, I do have a little thing that's different on this one because the solutions are not going to be irrational. They're not going to be real. They're going to be complex numbers. So this is also a third possible thing that could happen after using synthetic division and trying to figure out what the two remaining zeros are to the equation, to the quadratic equation. So we're given that x equals negative 3 as a root, which again means that x plus 3 is a factor. And again, it's not that it's helpful knowing that x plus 3 is a factor in this scenario. I just want to review again that idea. But knowing that x plus 3 is a factor doesn't change the way that we do this. Since we know that x equals to negative 3, we're going to write negative 3 on the outside of our synthetic division setup. And our coefficients are 1, negative 4, and positive 24. And let's go through the technique. So we bring down the 1 and multiply 1 with negative 3 and add. That's going to be negative 4. Multiply, that's 12. Add, that's 8. Multiply, and then add, and we get 0. Again, this is probably not factorable. Like I told you, not probably. This is not factorable. So we're going to just jump straight into the quadratic formula. So I'm going to label this as A, B, and C. And do that again over here. So the negative of negative 4 is positive 4, plus or minus that 4 to the negative 4 to the second power is 16, and then minus 4 times the value of A times the value of C divided by 2 times the value of A, which is just 2. So let's see what we have here, okay? So let me just scoot over. And now let's pay attention to our discriminants. Well, our discriminant here is going to end up being negative 16. I plug this into our calculator and we end up with a total of negative 16 divided by 2. Now, this is exactly what I was referring to. This is not going to be a real number. This is going to be a complex number because we're trying to take the square root of a negative 16, which is not real. Since the square root of positive 16 is 4, the square root of negative 16 is going to be the imaginary value of 4. So we're going to call that 4i. Now, since they do have a common factor of 2, this term and this term do have a common factor of 2, I can reduce this fraction by dividing both of these values by 2. So we end up with 2 plus or minus 2i. And those are going to be the two remaining roots to this polynomial function, okay? So what this means is that if I was to graph this, because these numbers are imaginary, I would see that the graph to this polynomial function only crosses the x-axis at -3 and nowhere else. It goes up, it curves down, then goes back up, but it's only crossing the x-axis at this x value that was provided, this rational x value of -3. The other two positions, again, do not touch the x-axis, hence why they're complex values, okay? So we end up with complex solutions, which can also be written as separately as 2 plus 2i, and then 2 minus 2i. It's conjugate of 2 minus 2i. But if you want to write it again using the plus and minus symbol, like I mentioned earlier, you could just do the exact same thing. Put the plus sign, click on your plus sign, and then click on the minus sign immediately afterwards, and that will make that symbol right there. I don't think you could find it as an icon to select from to include it there, but then again, I'm not too sure. But if you don't see it, you could still insert it by doing exactly what I said, or the other option is to simply do this, write it as two separate numbers using a comma in between. Now in this example, we are given, again, the information. We're trying to do the exact same thing, figure out what the two other x-intercepts are, but instead of straight out telling you, okay, that x equals to this, I'm giving you a graph, and you need to be able to dissect that, finding the value that makes this equation, this function, equal to 0, is simply going to be our x-intercept. And since a portion of the graph tells us that we're crossing the x-axis at +2, x equals +2, that's going to be one of our solutions. So if I plug in, let's say that f of x equals x cubed plus 2x squared minus 5x minus 6, and I plug in the number 2 here, that's going to make this entire thing equal to 0, okay? And I get that information by finding what the x-intercept is. So since that is a solution, let's now do synthetic division to get the quotient to this cubic function, which will be a quadratic, and then solving and finding out what makes that quadratic equal to 0. So 1, 2, -5, -6, bring down the 1, multiply, that's 4, multiply, that's 3, multiply, and again that equals to 0. So now with this quadratic equation, x squared plus 4x plus 3, let's see if we could do this by factoring. Let's find out what makes this equal to 0. And hopefully factoring works and we don't have to use the quadratic formula. So x plus plus, that's easy because they're both plus. And our factor is 3, which is a prime number. So only 3 divides itself. So 1 times 3. And that does work. 1 times 3 is equal to 3. And more importantly, 3 plus 1 equals to 4. So here factorization does work, and I don't have to use the quadratic formula. So that means that x equals to negative 3 and x equals negative 1. So these are the other two places where the graph, or I'm sorry, where this equation will equal to 0. Now we're going to try to do the exact same thing in example B. We need to figure out what's going to make this thing equal to 0. Okay, so what x values can make this equal to 0? So I'm looking at the x value and just simply checking when we get 0. So not this one, because this one again is negative 6. That one's there on purpose to trick you, thinking that one of the values is negative 6. It's the other way around. I'm looking for the x value where the output value is 0. So if f of x is equal to this value right there, when I plug in the number 1, according to the table, my answer has to be 0. So that's the solution. So x equals 1 is a solution to this equation, which means that if I do a synthetic division problem with 1, I should end up with a remainder of 0. So we have 2, 11, negative 7, and negative 6. I'm going to bring down the 2, multiply, add, multiply, add, multiply, that's positive 6, and I do end up with 0. Now, I'm not going to even bother using factoring technique. I'm just going to plug this straight into the quadratic formula, a, b, and c. And not because I don't think it's not factorable, it's just because I don't want to deal with the whole technique of using this 2, multiplying it with 6, and going through that whole procedure. I'm just going to jump straight into the quadratic formula because it works 100% of the time. So negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times the value of a. So we have negative b plus or minus b to the second power. That's going to be 13 to the second power, which is 169, minus 4 times 2 times 6. And that will be divided by 2 times 2, which is 4. Again, 2a, 2 times 2, 4. Oh, I forgot to change this. This should have been 13, negative 13. Because the b value is 13, the negative of positive 13 is negative 13. Now let's see what the discriminant equals. So let's simplify this right here. So our discriminant is going to be a perfect square. It's equal to 121. So x equals negative 13 plus or minus the square root of 121 divided by 4. Let me move that down a little bit. It's too close to the previous row right there, okay? So there is my answer. Now, since 121 is a perfect square, I can take the square root of 121. I can now take the square root of 121, which is going to equal to 11. So that means that negative 13 will be added with 11, subtracted by 11, and then divided by 4. So we have two possible solutions. So let's do negative 13 plus 11. So negative 13 plus 11, that's going to give us a value of negative 2. Negative 2 divided by 4, that's negative 1/2. So that's one solution, negative 1 divided by 2. But if I do negative 13 and I now subtract 11, that's going to be negative 24. And negative 24, that negative 24 divided by the 4, that's going to be negative 6. So there's your other solution. So the two remaining solutions, and I'm not going to write it down, I'm just going to box them in right here, are these two values. So x equals negative 1/2 and x equals negative 6 are the other two places where this function will equal to 0. So it equals to 0 when x is 1 and when x equals to those two values right there. Okay. And again, look at this. I'm glad that I used the quadratic formula to show you that since we do end up with a perfect square, taking the square root of this value is equal to a decimal value, I can still use it to figure out what the rational values were, okay? So factorization was an option here. Factorization would work, but I didn't want to deal with the whole multiplying these two values, gain 12, looking for the factors of 12, which one too many, and see which one gives me 13, and then dividing those values by the 2 to undo it. Just plugging into the quadratic formula finds me those answers. And again, the square root of 121 was 11, and we can then add 11 with negative 13 and divide it by 4 to get this number, or I can subtract 11 from negative 13 and divide that value by 4, and we get negative 6. Well, that concludes the first part, again, to 5.5. I hope this video was helpful. I'm glad that you watched it, and like always, I hope you have a good day. Goodbye.